Section 6.2 now is what we're on. So this is about properties of sets. We have 4 things to talk about. The first is some subset relations. There's going to be a couple properties about subsets specifically. And then we're going to list out a whole bunch of set identities. We're going to prove 1 or 2 of them. You're going to prove a couple more in the homework, but these are going to be useful in your other proofs. And then, so that's what our third objective is proving set identities. And the last thing is we're going to talk a little bit more about the uniqueness of the empty set. So let's start out with our subset relations. So the first one we have, for all sets A and B, A intersect B is a subset of A, and A intersect B is a subset of B. So these are all 3 of these that we're going to look at here are pretty straightforward. If I take everything that's in A and everything that's in B, every element in this set is still an element of A, so it makes sense that it should be a subset of A. And everything in this set is still a subset of B because we took things from A and B, so this is a subset of B. So that's pretty straightforward, I think. The next one is for all sets A and B. A union B is the thing we're building, and it turns out that A is a subset of A union B. And B also has to be a subset of A union B. Because our union takes everything from A and everything from B, so it makes sense that everything in A is here, and everything in B is also here. And our last subset relation for all sets A, B, and C, A is a subset of B, and B is a subset of C. Well, this is nothing more than our transitivity property. Whoops, not B. A is also a subset of C. Everything in A is in B, everything in B is in C, so that means that everything in A is also in C. Just standard transitivity. So we're going to do a quick little proof of the first relation here. And I say quick because it's about 1 line. So we're going to prove for all sets A and B, A intersect B is a subset of A. Like I said, this is a very, very short one. So short I can fit it into this little space. So the first thing we're going to do, let X be an element of A intersect B. So by definition, then X is an element of A and X is an element of B. Well, we're using our specialization because our intersection is our conjunction. So X is in A and X is in B. We can therefore say that X is in A, specializing, And so X and A means that A intersect B is a subset of A, because we took an arbitrary element in the intersection and showed that that element is also an A. And you can see the proof for the other side, for the showing that B, replacing A with B here, it's the exact same proof, except here instead of specializing to A, we specialize to B, and we have the result. So quick, painless, easy to see. We can do another quick proof here. We can prove the transitivity property. So for all sets A, B, and C, if A is a subset of B and B is a subset of C, then A is a subset of C. So I recommend you try this one. We've proved the transitivity property a couple times over the semester, so go ahead and pause the video and try this out. Remember, we're using the element method. So our first statement needs to let X be an element of A and let A be a subset of B and B a subset of C. Those are hypotheses. So by definition, of subsets, X is an element of A means that X is an element of B, and X is an element of B means that X is an element of C. So A is a subset of C. This again was since X was arbitrary. That's the proof. And I believe the second relation, you may prove one or both parts of that in the homework. But it's a pretty straightforward proof just like these. And really what we want to get to is our set identities. Identities. So these are kind of the building blocks of our set identities, these three relations. And we're going to let A, B, C be subsets of the universal set U for our set identities. And like I said, we have a whole bunch of these. Now we're just going to list them out. I have about 12 of them here. So the first is A union B is B union A, and A intersect B is B intersect A. And so this is commutativity. If you union two sets, it doesn't matter which one came first. If you intersect two sets, it doesn't matter which one came first. The second identity, parentheses A union B union C equals A union, parentheses, B union C, and A intersect B, in parentheses, intersected with C, equals A intersected with the parentheses B intersects C. So this is our associativity property. If you take everything from A and everything with B, and then you couple all of those things with everything from C, well, it's the same as taking everything from A and coupling that with everything from B and everything with C. Same thing with the intersection. If you take the things that are just in A and B, and then you intersect those with the things that are in C, that's the same as if you took the things that are just in B and C and intersected them with the things in A. It all works out the same. Our third property is A union B intersect C in parentheses equals parentheses A union B intersect A union, whoops, not intersect, union C. So you can think of this as distributivity. You only distribute union to intersect, and you can also distribute A intersect B union C, and this becomes A intersect B union A intersect C. So the symbol that is outside the parentheses goes inside, and the symbol that's inside goes outside once you distribute. And this is our distributive property for sets. The next property is A union the empty set equals A, and A intersect the universal also equals A. So this is our identity property, essentially. If you add the identity, nothing, to A, you end up with A, and if you intersect A with everything, you still only end up with A. The next one we saw is A union A complement. This is going to equal our universal, and its partner identity is A intersect A complement. Well, if you take everything that's an A and you intersect it with everything that's not an A, you're left with nothing, the empty set. Okay. Next one, if you take the complement of a complement, so this is everything, A complement is everything not in A, so the complement of A complement is everything not in the set of everything that's not in A, and that's just A again. Number 7 here, A union A is just A, and A intersect A is also just A. If you take everything from A and you combine it with everything from A, you still only have things from A. And if you take everything with A and then you intersect it with everything in A, you're going to be left with everything. So both of these equal A. Excuse me. Number 8 here, A union the universal is going to equal the universal, and A intersect the empty set is going to equal the empty set. So if you union everything from your universal set with a subset, you have everything in that universal. And if you intersect any set with nothing, you still have nothing, because there's nothing to actually intersect with. Number 9 here is parentheses A union B complement is equal to A complement intersect B complement. This is everything in A, and this is everything in B. So we want everything that's not in A and not in B. So that's everything not in A and everything not in B. And then we also have the complement of A intersect B This is everything in A and B. And so the complement is everything not in A and B. So you can think of this as negating the conjunction, and we know that's going to give us the disjunction. Everything in A, or everything not in A, or everything not in B. So A intersect B complement is A complement union B complement. Number 10 here, A union A intersect B. Well, this is everything in A plus everything that's in A and B. That's just going to give us A. Because everything here is A, everything here is A. So everything is still A. And we have a similar result, A intersect A union B. Well, this is everything from A and B, and then you're only taking the elements that are also in A, but since everything in A is here, this is still equal to A. Number 11 here, the complement of the universal of A universal is the empty set, and the complement of the empty set is a universal set. And then the last one again is one that we saw, A minus B is A intersected with B complement. So those are our 12 identities for sets. There are lots and lots of identities just like you're used to in every math class. There's always more than we do. Some of them become less useful because they're needed just for specific things. So we're just going to walk through the proof of one or two of these. So we are going to prove identity 3A. That is A union B intersect C equals A union B intersect A union C. So we're doing set equality, which means we need to show that this is a subset of this, and then that this is a subset of this. That's going to be how our proof starts. So we are going to here show that A union B intersect C is a subset of A union B intersect A union C. And for these set equalities, I do recommend you write what you're showing just to format your proof so you know where you are, and it makes it easier for me to look at as well. So we're going to let X be an element of A union B intersect C. So then X is in A, or X is in B intersect C. So that means we have cases. So case 1, X is in A. Well, if X is in A, this means that X is in A union B. This is generalization. If I'm in this, then I'm certainly in the union. And X is in A union C. That's just using a definition of the union. So this is by definition of union. So if I'm here and I'm here, then X must be in A union B intersected with A union C, again by definition of intersection this time. Intersection says you have to be in both. Well, we're in both, which means that we're in the intersection. So that's case 1. We were in A. Case 2, X is in B intersect C. If we're in the intersection, then that means that X is in B and X is in C. This is by definition of intersection. Intersection. And then if we're in B and we're in C, well then X is in B union A and X is in C union A. Again, this is just by definition of union. So if we're in B union A and we're in C union A, we know by the identity B union A equals A union B, and B, whoops, not B anymore, C union A equals A union C. So X is in A union B and X is in A union C. Therefore, X is in A union B intersected with A union C. And again, this is by definition of intersection. So, in both cases, if X is in A union B intersect C, then X is in A union B intersect A union C. So we have our subset. A union B intersect C is a subset of A union B intersect A union C. Whoops. Just supposed to be the union symbol. So we have half of our proof. So now we're going to move on to show that A union B intersected with A union C is a subset of A union B intersect C. Lost my train of thought for a second. So we're going to let X be an A union B intersect A union C. So by definition of intersection, we know that X is in A union B and X is in A union C. And this is just by definition of intersection. So this means that X is in A or X is in B, and X is in A or X is in C. So there's a lot of combinations here, but really what this boils down to is either X is in A or X is not in A. Because if X is in A here, then X is in A here. And if X is not in A here and X is in B, then X is not in A here. So you see how that works? Since this is a conjunction here, if we're in A, then we're in A in both, because our A's isn't changing. And if we're not in A, then we're not in A. So our cases, the first is X is in A. So by definition, of union, X is in A union any other set that we want, and we want B intersect C. Easy peasy. Case 2, X is not in A. Well, if X is not in A, then X is in B and X is in C. And X is in C. So by definition of intersection, X is in B intersect C. So if X is in B intersect C, then by definition of union, X is in B intersect C, union A, or using our identity, X is in A union B intersect C. So in either case, come now, paper, work with me. In either case, if X is in A union B intersect A union C, well, then X is in A union B intersect C. So we have our subset. A union B intersect A union C is a subset of A union B intersect C. I wrote union here again. This should be intersect. So since both subsets are, or since both sets are subsets of each other, are subsets of each other, A union B intersect C will equal A union B intersect A union C. And we have our proof. So we're going to do a couple more here, and then we'll talk about, well, actually, let's go ahead and combine some of these things. So we want to prove one more identity and then prove the identities that involve the empty set, or a couple of them at least. So we can really dive into what the empty set is all about. So we're going to prove if A is a subset of B, then A intersect B equals A, and A union B equals B. So this is going to have two parts. I know I have it written as a conjunction, but we're just going to prove if A is a subset of B, then the intersection is A, and then if A is a subset of B, the union is B. So we're going to split this into two proofs. Now, I highly recommend you try this one on your own. It's not quite as long as the last one, and it's pretty straightforward. So we're going to start our proof here. And the first part I'll be doing is that A is a subset of B implies that A intersect B equals A. And so this is what we are proving. So we're doing set equality, which means I want to show that A intersect B is a subset of A. So we're going to let X be an A intersect B. By definition, then X is in A. So A intersect B is a subset of A. We took an element from one and showed it was in the other. Now we want to show that A is a subset of A intersect B. Now this part requires the initial hypothesis. So we're going to let X be an A and A be a subset of B. So by definition of subsets, if X is an A, if X is an A, then X is in B. So X is in A and X is in B. This means that X is in A intersect B. Thus, A is a subset of A intersect B. And so this proof here is not possible if we don't have the initial A is a subset of B, because we know that A intersect B is smaller than A. So the only way that A is a subset of an intersection is if A is completely contained in whatever is being intersected. Right? So without this subset, A is a subset of B, this proof goes nowhere. But this is our proof. We have set equality. So since one way you'll see this is containments. So since both containments are shown, A intersect B equals A. Because that's really what we're talking about when we say subset. We're saying that A is contained in this set. A is contained in B, A is contained in A intersect B, A intersect B is contained in A. So you'll see this phrase a lot. So the next one, part B here, starting a whole new proof, and we are proving that A union B equals B. So we are going to show that A union B is a subset of B. So we let X be in B, or X be in A union B, then that means that X is in A or X is in B. Now, it looks like this should be cases, and technically it is, but a lot of times you'll see these types of cases not actually written in the case format, and that's because if we let X be in A, then since A is a subset of B, remember that's our initial hypothesis. Oh, that means that I wrote this wrong. We're showing A is a subset of B implies A union B equals B. So since A is a subset of B, X is in B. Well, then A union B is a subset of B. And case 2, X is in B. So then A union B is a subset of B. In either case, A union B is a subset of B. All right, so this case 2 really isn't a case because it's our result. So really the only thing you need to show is if you are not initially in B, that you're still in B. Because if you are in B, then you're a subset. So we need to show that all of them are true. So that's the way we can do that. So now we need to show that B is a subset of A union B. So we're going to let X be in B. Then, by definition of union, X is in A union B. Because union is disjunction. So if I'm in one, I'm certainly in the union. Thus, B is a subset of A union B. And again, since both containments have been shown, B equals A union B. That's our proof. So a lot of these proofs are just fitting the definitions and the identities into the right order. And a lot of them, once you see how it needs to go, like in this one, as long as you remember how to prove set equality, showing a subset and showing another subset here, then it's just, like I said, fitting those things into place properly. So let's look at a couple proofs here that deal with the empty set. So the first one, we're going to prove that the empty set is a subset of A for all sets A. Now this is actually really hard to show directly because, as we know, the empty set is the set of nothing, which means that we have nothing to use the element method. So what we are going to do is use a contradiction. So we're going to suppose not. That is, suppose there exists some X in the empty set such that X is not in A. Well, this is the great thing about the empty set, which makes it So unique is, right now, our supposition is a contradiction, because we're saying that there is an element in the empty set. But we know there does not exist an X in the empty set. And this is at all, because it's empty. And this is a contradiction. So the empty set is a subset of A for all sets A. Interesting little proof here. But that is something that we can use. The empty set is always a subset. So every set, we usually say, has two subsets. So this is a, you can think of this as an extra identity. It's not really an identity, it's a property. But for all sets A, there are at least two subsets. That's not the right two. Two subsets. The empty set is always a subset, as we just proved. And the set itself is an improper subset. And when your set A happens to be the empty set, well, then these two things collapse into the same property. But you can always have minimum two subsets, the subset of nothing and the subset of everything. And it turns out if you have a non-trivial set, a non-empty set, you always have at least more than these two. So let's prove arguably the most important property of the empty set. There is only one set with no elements. And what this means is that our empty set is unique. There's not multiple empty sets, there's just the empty sets. So we're going to do this one. Again, the empty set is hard to do things directly with because there's nothing to work with. So we're going to suppose not. That is, let E1 and E2 be two sets with no elements. So, by the previous proof, we know that E1, which is empty, will be a subset of every other set, including E2, and E2 will be a subset of every set, including E1. So, E1 equals E2. And that's our proof, because this is a contradiction. So I guess if we want to be perfect here, we should have different sets. To make that clear, so we're supposing that E1 and E2 are two different sets. And our contradiction is that they're not different. They're not different, they're the same. So our empty set is unique, and it's the subset of every other set. And we're going to do 2 more empty set proofs here. So the next one is one of our identities. So we're going to prove for all sets A intersect the empty set equals the empty set. So I encourage you to try this one on your own. Pause the video and try it out. I will tell you that this proof is going to be easier to do using contradiction. So pause now. Okay, great. So we're going to suppose not. That is, there exists some x in A intersect the empty set. That's what that means. So if this is not true, then it's non-empty, which means that there's some element in there. Well, by definition of intersection, x is in A and x is in the empty set. But by definition, for all x, x is not in the empty set, which is a contradiction. So we have a contradiction. I don't need that. A intersect the empty set must equal the empty set. Right. So you can kind of see from these last couple proofs that the empty set, it lends itself really well to contradiction proofs, because if you can show that something's in the empty set, you have a bona fide contradiction immediately. So a lot of times when you're proving set identities, if you're trying to do a contradiction, the contradiction you're most often going to come to is that either your element is in something and not in that same thing. So either you're in A and you're not in A. That's a contradiction. Or you have any element in that empty set. Because as soon as you can get this statement in any proof, that's a contradiction. So if you're doing it by contradiction, great. If you're doing something directly and you end up with this, it means you probably have gone wrong somewhere and you want to take a look at where that is. So our last proof with the empty set here is going to be for all sets A, B, and C. If A is a subset of B and B is a subset of C complement, then A intersect C is the empty set. So we can actually do this directly and indirectly. So we'll do both versions. So let's start with the direct proof. We'll let A, B, and C be sets such that A is a subset of B and B is a subset of C complement. Then, by transitivity, we know that A is a subset of C complement. So this means for all x, that are in A, x is in C complement, which, by definition, of complements, So if we're in C complement is all the things that are not in C. So this means for all x in A, x is not in C. That's what it means to be in the complement. Well then, x is in A and x is not in C. So by definition of intersection, x cannot be in A intersects C. Because if you're in A intersects C, then you have to be in C, and we're strictly not in C. And so that means for all x in A intersects C is empty. And that's it. Now we could do this with set equality. If you pick something that's in the empty set, you have to show that A intersects C is empty, which is exactly what we did. And if you pick something in A intersects C, you need to show that, again, A intersects C is empty, and that's what we did. So our proof is complete. Now again, that's the direct proof. So let's look at how we do this indirectly. So suppose not. That is, for sets A, B, and C, let A be a subset of B, and B be a subset of C complement, and A intersect C is non-empty. Well, then that means that there exists, let's call it X star in A intersects C. So X star is in A and X star is in C. But by transitivity again, A is a subset of C complement. So if X star is in C complement, or if X star is in A, then X star is in C complement. And if X star is in C complement, X star is not in C, but we already know that X star is in C, a contradiction. Therefore, A intersects C must equal the empty set. So this is, like I said, your classic contradiction. You're not in a set and you're in that set, or you have something in the empty set, which is what we're doing. So 2 different proofs, indirect versus direct. That is the end of 6.2. Your homework's going to have lots of fun little set proofs and set identities to prove. So you'll take care of those then.